Can you see the screen?
Yes, sir.
Okay, you can start.
Good morning, everyone. I'm here to give the presentation on flip-flop conversions. To make any type of conversion, first we need to know the excitation and characteristic table of required flip-flops. I'll start with the conversion of JK flip-flop to D flip-flop. To convert JK to D flip-flop, we require the excitation table of JK flip-flop and characteristic table of D flip-flop. First, write down the essential excitation table of JK flip-flop. Then write down the characteristic table of D flip-flop. Observing the Qn and Qn plus 1 terms in the JK flip-flop, write the terms of J and K. For 0, 0, it is 0 and invalid. For 0, 1, it is 1 and invalid. For 1, 0, it is invalid and 1. For 1, 1, it is invalid and 0. Then we have to draw the K maps for J and K. The inputs are Qn and D, so we'll get a two variable K map. For J, a pair is formed and the equivalent is D. For K, the equivalent is D bar. Then draw the logic diagram using this obtained relations in the K maps. Here we are converting JK to D. So connect D to J and D bar to K. This is a required conversion. To convert SR flip-flop to T flip-flop, we require the excitation table of SR flip-flop and characteristic table of T flip-flop. First write down the excitation table of SR flip-flop and then write down the characteristic table of T flip-flop. Observing the Qn and Qn plus terms from the SR flip-flop, write down the terms in this excitation characteristic table. For 0, 0, the equivalent is 0 and invalid condition. For 0, 1, it is 1, 0. For 1, 1, invalid and 0. For 1, 0, it is 0 and 1. Then draw the K maps for S and R. Since the inputs are Qn and T, we'll get the two variable K map. For S, one single, the equivalent of that single is Qn bar into T. For R also one single is formed and the equivalent is Qn into T. Here we are converting SR to T. So the logic diagram will be, we have to connect Qn bar into T to S. Qn bar into T means connect the T and Qn bar with an AND gate and give that to S. For R, connect Qn and T with an AND gate and then give that to R. This will be the required logic diagram. For the conversion of SR flip-flop to JK flip-flop, we require the excitation table of SR flip-flop and characteristic table of JK flip-flop. First write excitation table of SR flip-flop, then write the characteristic table of JK flip-flop. By observing the present and next state terms, write down the terms for S and R. For 0, 0, the equivalent is 0 and invalid condition. For 0, 0, again invalid, 0 and invalid. For 0, 1, it is 1, 0. For 0, 1, again 1, 0. For 1, 1, it is invalid and 0. For 1, 0, 0 and 1. For 1, 1, valid and 0. For 1, 0, it is 0 and 1. Then draw K maps for S and R. Since the inputs are Q and J and K, will be getting a 3 variable K map. So here the midterms are 2 and 3. A pair is formed and the equivalent of that is Q1 bar and the common term 1, 1 and 1, 0 is 1. That will be J. So Q1 bar into J will be the equivalent for S. Similarly, draw the K map for R. Here also the midterms are 5 and 7. A pair is formed. For this Q1 into in 0, 1 and 1, 1, 1 is common. That 1 is for K. So the equivalent for R will be Qm into K. This is the logic diagram. First draw an AND gate using Qn bar and J. And then
Srini, explain SR flip-flop to D. Rule number 71. Or else Kirtana. Rule number 66.
So,
Explain this one, Kirtana. SR flip-flop to D conversion.
for SR flip-flop to D flip-flop, first we should construct a characteristic table of SRFF. SR flip-flop
Characteristic or excitation of SR?
excitation.
Exaggeration.
First excitation table of SR flip-flop. Next. What is the next step?
Characteristic table of DFF.
Okay, characteristic table of D flip-flop. What is the characteristic table of D flip-flop? It gives relationship between
Qn, Qn plus 1 and D.
characteristic table Qn, D and Qn plus 1. Tell me the characteristic table.
0, 0.
0 and 1, 0.
Okay. How you are getting the output? How I am getting the
0,
output? Okay.
0, 0, 0. 0, 1, 1. 1, 0, 0. 1, 1, 1.
How you got this one?
Excitation table.
This characteristic table of D flip-flop is depending on what?
Table. D flip flop.
Exaggeration table of SRFF.
Characteristic table of D flip-flop is depending upon truth table of D flip-flop. Okay, done. So we wrote Qn, D, Qn plus 1. Okay, done with the two steps. Next, what I have to do?
Came SR flip-flop.
Okay, so write SR here. So next, what should I do? You need to compare
Q and Qn plus 1
Characteristic table
with
to
S.
exaggeration table.
Okay, so compare 0, 0. Output is 0x.
0 and not valid.
Next 0, 1. See here 0, 1, it is 1, 0.
1, 0.
Next,
1,
what is
0,
1?
0, 1.
Okay,
1, 1,
next,
X 0.
done. Next, after this,
K map
K map for S and R.
do the K map for S and R. So is this correct or any modifications? 2 variable K map or 3 variable K map?
2 variable.
2 variable
K
map.
So 2 variable K map Q and D you need to take. So Qn followed by D. And what are the minterms for S and R? Tell me the minterms for S. Sum of minterms are
1 and 3.
1, sir. Don't care is 3.
1 plus don't care is 3. Next for R,
2.
2 is min term and don't care is 0.
0.
2 is
0.
minterm and don't care is 0. So that what you need to plot here. So 1 followed by 3 is don't care. Here 2 followed by 0 is a don't care. So try to group them so that a pair will be formed and try to write the equivalent for this. So answer for this will be D. For this it will be D bar. So S is equal to D and R is equal to D bar. After this,
logical
Logic
diagram.
diagram.
logic diagram. So here the first one is nothing but SR and the second one is nothing but D. We are trying to convert SR flip-flop into D flip-flop. So for SR flip-flop, what are the input modifications that you need to do so that it will function as a D flip-flop?
We need to
So
input
for
D.
S, correct.
S is
So for
equal
S
to D.
and for R it should be D bar. So not gate. Okay, next. Ankita, explain JK flip-flop to T. Not there. Next rule number 45. Not 45, 44. Anusha. JK flip-flop to T flip-flop conversion. Rule number 38. Samir, are you there? Rule number 38. Okay. So Meghana, continue. Next.
Yes, sir.
So I think
To
it is
convert.
clear. All the concepts will be same like this only.
Yes, sir.
So simply write the excitation table for this one followed by characteristic table. So better you need to remember all the characteristic table, excitation tables and truth tables of all the flip-flops. So one question is guarantee among these conversions. So the important thing is drawing this logic diagram is very important.
Sir, for long answer, sir.
For long answer. Mostly for
Sir,
7 marks
explain
will
logic
get conversion.
diagram now.
Logic diagram. Which one you want?
This one only, sir.
This one for JK to T. I think from CSEB Samira has one doubt in flip-flop. May I know that question? So T flip-flop 2, I mean JK flip-flop, I want to convert this one into T flip-flop. So for JK flip-flop, write the excitation table, and for T flip-flop, write characteristic table. So characteristic table means it gives relationship between Qn, T and Qn plus 1. Now by seeing Qn and Qn plus 1, we need to write the output, which are nothing but J and K. So after doing this, do the K map for J followed by K map for K. So if you do the K map, you will get some Boolean expression. So I got here answer as J is equal to T and K is equal to
K
T.
is also
Same.
equal to T.
So here the given flip-flop is nothing but JK flip-flop. So I know JK flip-flop, but I want to make that JK into T. Means what are the input modifications that I need to do so that this particular JK flip-flop will function as T. So first draw that JK flip-flop. So J and K are inputs, Qn complement or else Q bar, anything you can take. These are the outputs and clock should be applied because it is synchronous. Apply these inputs. J should be connected to T. External input. T is nothing but external input followed by K is again T. So connect T. Now this particular JK flip-flop will function as T flip-flop.
Oh, okay, sir.
Okay. We are having JK. I want to make it as T. So these are the modifications that I need to do. Same concept is applicable for everything. JK flip-flop to SR flip-flop. So here the given flip-flop is nothing but JK. So what are the modifications that I need to do for JK so that it will function as SR? Means based upon the K map answers, we need to make the modifications. So J should be connected to S, K should be connected to R. Alright, so almost 12 conversions will be there. So all 12 concepts are covered. So try to practice. Next, who else? Patan, are you ready? Rule number 5. Sanjana, rule number 76.
Sir, on Monday.
On Monday. Okay. So if that's the case, I'll go with the next concept which is left, that is CPL.
So
What is the full form of PLD?
once
Yes.
explain asynchronous method, sir.
Once explain asynchronous. What asynchronous? Asynchronous inputs or asynchronous counters?
4 bits T flip flops, sir.
4-bit T flip-flop asynchronous.
Up and down or down?
Okay. Asynchronous counter. In this up counter, designing you want using T flip-flop. So for asynchronous, I told you to remember one trick. What is that? Up counter, opposite sign or same sign?
Up counter is opposite sign, down
down
sign.
Opposite sign.
Down is same, sir.
So
Down
what
is
I
same
is
sign.
everyone are doing a mistake in asynchronous counters. For asynchronous also they are doing the same method as synchronous, which is wrong. So here this is a trick which you need to follow. For 2-bit, 3-bit and 4-bit diagrams will be the same. So flip-flop is of size 1 bit, so as it is of size 2-bit, so take 2 flip-flops. It can be either JK or T. So 2 flip-flops are there. I'm taking this as TA. This is QA, QA bar. Next one will be TB, QB and QB complement. And what is the clock you want to take? Positive edge trigger or negative edge trigger?
Negative, sir.
You want negative. So take negative edge trigger. Negative edge trigger means bubble will be there outside followed by a triangle. Here also same thing. And here the important thing is T should be connected to logic 1. Why?
Should have same output.
Why T should be connected to logic 1? If it is JK, JK should be connected to logic 1. Yes, always output should get changed or else you won't get the output. So that's the reason all the T inputs are connected to logic 1. This is the first step. And you want to design up counter. So up counter is nothing but opposite sign. So here this is clock which is of sign negative, whereas QA is nothing but positive. QA bar is negative. So I want opposite sign. Opposite sign means here negative is there. This negative should be connected to positive so that it becomes opposite sign. So this is the diagram and I want the output so that this is QA. This will be
QB.
Or this is asynchronous counter up using T flip-flop. The same thing if you want to design using, suppose let me design the down counter now. The diagram will be same. What will be the modification?
The QA bar will be connected.
Same sign.
Connect.
Just
The
connect same
clock will be significant, the positive and negative.
Sir,
Will there be
internally
any
same
effect on the
number,
clock?
Positive, negative will be connected to negative only.
Okay, so QB, this is QB bar. Again, I'm going for negative edge trigger only. And TA, TB should be connected to logic 1. This is default. Now I want to perform down counter. So down counter is nothing but same sign. So here clock which is of type negative. So same sign means it should be connected to QA bar, correct?
Yes.
Yes, sir.
Now this will function as down counter and again output should be taken at QA and
QB.
QB. Important thing here is this is least significant bit, this is most significant bit. Now you want to design up down. Now tell me for up down counter.
We have to take the mod, sir.
Correct. We have to take mod or mode.
Mode.
It
MOD.
is mode.
I think
So it mode signal either it can be 0 or 1.
Or 1.
You write a clear note. If it is 0, you want to perform up counting. If it is 1, you want to perform down counting. Now, for this, how should I represent the Boolean expression? I want both up counting as well as down counting within a single design. It depends upon the type of triggering that you are taking. So let me design for negative edge trigger. Tell me how will you do for negative edge trigger. I'll draw 2 flip-flops again. This is TA, QA and QA bar. Next it will be TB, QB and QB bar. We are going for negative edge trigger. Till here it is common. Now tell me what should I do. Again TA, TB connected to logic 1. Tell me what should I do.
taking a mode signal, I mean input, and connecting
Okay.
an XOR gate to the output. I mean
Okay,
next.
first let us design by using basic gates. Use basic gates and tell me how many basic gates are needed.
Two AND gates and one OR gate.
2 AND gates and 1 OR gate. So what should be applied for AND gate?
For up counting, we should connect it from up in the sense opposite sign from negative QN bar, if QN bar and mode 0.
So you tell me what should I write here, QA or QA bar?
QA.
QA. This will be QA bar.
QA
So tell
bar.
me the
QA
Boolean expression. If m is equal to 0, you have to connect it to QA.
QA bar.
If m is equal to 1, it should be connected to QA bar. So that's the reason 2 AND gates followed by 1 OR gate. So this will be default for all the cases. So take 2 AND gates followed by 1 OR gate. That OR gate should be given to the clock and check the inputs. So one external signal called as mode signal you need to use, m followed by m bar. So this is m bar, this is m. So m bar, so connect m bar here, m bar QA, next one will be m QA bar. This will be m QA bar. Again, this diagram varies. Suppose if you are taking 0 for down counting and 1 for up counting. So better try to write the clear note. Like what is your assumption? If it is 0, you are performing up counting. 1.
M QA plus M bar QA bar B A
Just tell me m
QA plus M bar QA bar.
m bar QA bar. So this will be the condition. Suppose if m is equal to 0, 1. So for 0, if you want to perform down counting, and for 1, if you want to perform up counting. So try to remember this relationship. Mostly if you see all the different kinds of textbooks, you'll get confused. Why? Because this will be the only change. Our assumption is m is equal to 0 for up counting and 1 for down counting. If this is the case, m bar QA plus m QA bar. And again, this depends upon the type of triggering that you are applying. Remember that point also. Here, this is for negative edge trigger. Similarly, you can do this one for positive edge trigger also. Okay, so don't get confused with all the different kinds of concepts. Either you can go for 0 for down, 1 for up, or else 0 for up, 1 for down, and this is for negative edge trigger. Similarly, you can write for positive edge trigger also.
Sir, how you are getting that expression, sir?
This one,
Yes, sir. M bar QA plus M QA bar.
if m is equal to 0, what you are doing, up counting or down counting?
Up.
You are doing up counting. And for m is equal to 1,
Down counting.
you are doing down counting. And you are using negative edge trigger. So in negative edge trigger, if you want to perform up counting, what will you connect, QA or QA bar?
QA, opposite sign.
Up counting means opposite sign, down counting means same sign. So it should be
QA,
connected
sir.
QA. Here,
QA bar.
QA bar. So that's what I wrote. M is equal to 0. 0 means M bar. You can write as M bar. QA. This is nothing but M QA bar.
M QA bar.
So finally, you try to add them. Why? Because I want both up counting as well as down counting within a single design. So I'm trying to add them. So this is a relation that you need to know. Suppose if it is for positive edge trigger, you tell me no. Same condition I'll do. M is equal to 0, M is equal to 1. For 0, I want to perform up counting. For 1, I want to perform down counting. But here I'm going for positive edge trigger. Now what will
QA
you
bar for M equal to 0, sir.
Yes,
correct? Here it should be QA bar. Here it will be QA.
QA.
Now this becomes M
M
bar
bar QA plus MQA.
QA
MQA.
MQA.
So finally add them, M bar QA bar plus MQA. Both are correct only. Don't get confused. The thing is, he might make the changes in negative edge trigger or positive edge trigger, or else you can go for different cases for up down counter also. Our assumption is m is equal to 0 for up, 1 for down. So better for this question you write clearly like what is your assumption. And in asynchronous mod counters, I've seen most of the mistakes. So let me check that one. Okay, design mod 7 asynchronous up counter using SR flip-flop. So can we design asynchronous using SR flip-flop and D flip-flop?
No, sir.
Why? What is the reason? No is correct only, but reason.
Sir, racing condition, sir.
Yes, we are not getting racing. If you observe in SR flip-flop, if you write the truth table, Qn plus 1. So 0, 0, 0, 1, 1, 0, 1, 1. So it is Qn 0, 1, x. For 1, 1 condition, output is invalid. We are not even getting the output. So in order to overcome this, we went for JK flip-flop. In JK flip-flop, inputs are J and K, output is nothing but Qn plus 1. So this is 0, 0, 0, 1, 1, 0 and 1, 1. So here it is Qn 0, 1. And what was the last answer?
Qn bar.
It was Qn bar. So in order to convert SR into JK, we have added some extra kind of feedback from output to S followed by R. And similarly, if you see the truth table of T flip-flop, input is nothing but T, output is nothing but Qn plus 1. If you want, you can write the clock also. For 0, it will be Qn memory, and for 1, it will be Qn bar. So these two conditions are same. If you connect J is equal to K is equal to 1, or else T is equal to 1, output will change continuously. Whereas see here, for S is equal to 1 and R is equal to 1, output is invalid. You can't make use of this one. And similarly, if you check for D flip-flop, if input is 0, output will be 0. If input will be 1, output will be 1. So output is not getting changed. So you should not use SR flip-flop and D flip-flop to design asynchronous. Remember this point. So for T flip-flop and JK flip-flop, only you will find asynchronous. Why? Because JK should be connected to logic 1 and T should be connected to logic 1. So for asynchronous also, you are doing the same concept as synchronous, which is wrong. How will you design asynchronous counters? In asynchronous mod counters. So till now we have seen only asynchronous, which is up counter, down counter and up down counter. For asynchronous mod counters, what is the difference? Will you use the same flip-flops or else any modifications will be there? Do you know this?
Yes, sir.
So for asynchronous mod counters, this is what you need to use. You need to make use of asynchronous inputs. So what are asynchronous inputs? In short, he may ask, asynchronous inputs are nothing but preset and clear.
And clear.
Preset is also called as set, clear is also called as reset. I've explained you 4 different kinds of cases for this by taking bubbles and without taking the bubbles. So for asynchronous mod counters, this is a diagram that you need to use. Suppose if it is mod 7, how many flip-flops should I use for mod 7?
3 flip-flops, sir.
So we need to use 3 flip-flops. So how many outputs do I get?
3.
3 flip-flops, 3 outputs. How many combinations?
8.
8 combinations.
0, 1, 0, 0, 1, 1. Next one will be 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So I want mod 7. Mod 7 means what? Mod 7 I want. Means how many states will be there? 7 or 8?
7.
7.
So this 7 states, I want reset to be 0. Why reset to be 0? Why not 1? And here I need to take reset should be 1. Why? If reset is high, output will be?
Set is high.
0.
Output will be 0, sir.
Suppose if I take reset is equal to 0, will there be any effect on the output? There is no effect on the output if reset is equal to 0. So if reset is equal to 1, I'll get output as 1. As this is mod 7 counter, at this particular point of time, I want to reset. So that's the reason I'm activating reset pin. And for better understanding reset, here this is active high. This is called as active high reset. Suppose if it is active low reset, it will be represented like this, reset bar. In order to activate reset bar, will you apply 0 or 1? In order to
1.
activate reset, you want to activate reset bar.
0.
You need to apply 0 to activate. So in remaining positions, it will be 1.
Last position 0.
Last position, it will be 0. So don't get confused with these two cases. Active high followed by active low. Okay, if it is active high, to switch it on, apply 1. For active low, in order to switch it on, apply 0. So here only you will get confused. Active high and active low. So among these two, any one you can use. So let me go for active high case, so that I'll get last position as 1. Now apply K-map for this and tell me the Boolean expression. 3 variable K-map or 4 variable K-map?
3 variable.
3 variable K-map inputs are Q3, Q2 and Q1. All positions are 0, only 7 it should be 1. So 0, 1, 2, 3, 4, 5, 6, 7. Here it will be 1. And equivalent will be Q3, Q2 and Q1. Simply you can make use of one AND gate and apply it to the reset pin so that it will function as mod 7 asynchronous. Okay, so remember this carefully. If it is asynchronous modulus, by default you need to make use of asynchronous pins, which are nothing but preset followed by clear. So obviously synchronous counters are very easy. The only difficulty that you will face with this is this one only, asynchronous. In asynchronous also modulus. Whereas the normal asynchronous counters are very easy. Up counter directly you can draw the diagram. Down counter is same thing and up down counter is same. For up down counter by default 2 AND gates and 1 OR gate will be there. But here extra pins preset as well as clear you need to make use of. That's the only difference. Whereas if it is synchronous, in synchronous the sequence of procedures you need to follow depending upon the flip-flop, it again varies. Any other doubts still? So if you try to solve, you'll get the questions. Anything else?
No, sir.
So what is the full form of PLD?
Programmable logic device.
How many programmable logic devices are there? Tell me how will you design PROM and what is the full form of PROM?
Two types of PLDs are there, sir.
Okay, PROM full form is programmable
Read-only memory.
read-only memory. What is PAL?
Programmable array logic.
Programmable array logic. Next one,
Programmable logic array.
programmable logic array. And next, how will you design? What is meant by fixed and what is meant by programmable and how will you represent? Fixed means dot, programmable means X. Tell me for PROM, which one is fixed? Two arrays will be there, AND array and OR array.
Fixed AND array, programmable
Programmable OR array.
So this is fixed AND array and programmable OR. And what is the extra thing that you need to use to design fixed AND? Encoder, decoder, comparator, what you will use?
Decoder.
So decoder will be used. Remember this point. While correcting, they will check only these points. Next, what is PAL?
Programmable AND array and fixed OR array.
So here programmable and next one is fixed OR. Third one?
both are fixed. Both are programmable.
Both are
Programmable.
Programmable and programmable OR. So at least these 3 points, if you remember, it's enough. And fixed means represented with dot, programmable means X. And two types of arrays, AND array followed by OR array. So he will give you one Boolean expression, and for that you need to draw the logic diagram, or else he will give you one K-map, like some minterms will be given as a function of inputs. For that you need to do the K-map and try to draw the logic diagram. So again the same as unit number 1 and 2. So apart from this, there are two more types of PLDs are there. So structure of Cpld. What is the full form of Cpld now? You know about PLD. It is programmable logic device. What is C? It is complex programmable logic device. So it is nothing but the group of PLDs we will make use of. It can be either PAL or PLA. So structure of Cpld. A Cpld comprises of multiple PAL-like blocks on a single chip with programmable interconnect to connect to the block. What is meant by interconnect? What is meant by interconnect? What is meant by wire? What is meant by net? And what is meant by bus? Tell me the differences. All are same or all are different?
Same.
All these are same. Interconnect or wire or net or bus, everything will be same. So in Verilog program we wrote as REG. What is REG?
Register.
It is register. What is the difference between the register and wire? Difference between register and wire. Register will store the value.
stores
Whereas this one,
value.
this is just a connection.
Connect.
So wire, it will not store any kind of information, that just it will give the output of one as an input to another. That much only it will do. So Cpld architecture, it contains PAL-like blocks followed by programmable interconnect and IO blocks. So here IO block is nothing but input output blocks. PAL means programmable array logic, and here this is nothing but global. This is nothing but global. Means all the different components or blocks are connected to the single interconnect. So it is called as global programmable interconnect. This is the general structure of Cpld, which contains the combination of PAL and PLA blocks. So Cpld architecture is based upon small number of logic blocks and a global programmable interconnect. So instead of relying on programmable unit to configure chip, it is advantageous to be able to perform the programming while chip is still attached to its circuit board. So this method of programming is called as ISP, in system programming. It is not usually provided for PAL and PLA, but it is available for the more sophisticated chips like complex programmable logic device. Means, see this one. So HDL. HDL stands for, what is HDL?
Hardware description language.
It is called as hardware description language. So these are the sequence of procedures which we need to follow in order to write the Verilog code. Initially we will get some specifications, and based on that specification we will write the HDL code. Again you can write the HDL code either in the different styles of modeling, which can be either gate level, data flow, behavioral, or else switch level. And based upon the tool, if you write the code, we will get one fuse map called as some bit file. So what is this? It is called as IC. What is the IC number for operational amplifier? What is the IC number for operational amplifier, and how many pins will be there? Do you know operational amplifier? Is it there for you?
Yes.
Then what is the IC number? It is IC741, which is of 8 pins. And again different kinds of packages will be there, like dual inline package, metal can package, and all those. So in order to dump the code, we will place this particular IC into this universal programmable, and we will dump the code. So that depending upon our requirement, suppose if I wrote the Verilog code for half adder, then by using this universal programmable, I will dump the code. Now this IC, integrated circuit will function as an half adder, so that I can use this IC in any kind of application. So for every time if you want to dump the code, you need to bring this IC, you need to place on this universal programmable, and you need to dump the code always for each and every time. So these are the different kinds of devices that will make use of, which is called as ISP programmer. So here we will place our IC, and this is the VGA cable which will be connected to our PC, and we will dump the code. So in order to know about this, let me show you one video of how to do this procedure. So all these are not needed. So there is a tool called as Vivado apart from Xilinx. This is called as Fpga board, which can be used to dump all the different kinds of code. The simple thing is we need to write the Verilog code. So can you see the screen?
Yes, sir.
Okay, so simply we'll dump the code here. So we'll make use of a tool called as Vivado. In that we will write the Verilog code and we will get one bit file. So here if you observe here, this Arctic7 is nothing but our IC where our program will get stored. So by means of USB cable, we will dump this code so that depending upon our requirement, we can switch on this switches and we can see the LED lights at the output. So there are different kinds of functionalities can be implemented on this board. Whereas for the fixed logic gates, we can't do anything. So for AND gate, if we are giving input as 0, 0, output will be 0 only. It is default, means it is not programmable. Whereas these kits are nothing but programmable. Any kind of logic can be dumped on this so that it will work according to our functionality. So the Cpld architecture looks something like this. It consists of PLDs. PLDs can be either PAL or else PLA, followed by IOBs, input outputs. So input outputs are nothing but it can be either keyboard or else it can be the display monitor and so on. So just for the sake of dumping, we will make use of all this. And programmable interconnect. If you observe this horizontal and vertical wires, they are nothing but interconnect. So depending upon our logic diagram, it will make the necessary connections. Suppose if we want to function it as an half adder. So half adder contains how many gates and what are they? Half adder.
One AND gate and one OR gate.
It contains one XOR gate followed by one AND gate. So these gates followed by interconnections. So these are nothing but the interconnections that it will make use of. So in order to make that necessary connections, we will make use of this programmable interconnect. Whereas the thing is here PLDs will be present, which can be either PAL or else PLA. So it is nothing but a combination of the PLDs that we have seen. So nothing much concept will be there. The important thing, only thing is we need to remember this particular diagram structure of Cpld, which is complex PLD, which contains PLDs followed by interconnect as well as IO blocks. And how to program is universal programmer. So apart from this, we know all these concepts like PROM, PAL and PLA. We have covered all this. And the last thing that is left is FPGA, which is nothing but field programmable gate array. So this is a structure. So the only difference between the Cpld and FPGA will be in Cpld we will make use of PLDs. So here PLDs can be either PAL or else PLA. Whereas in field programmable gate array it contains CLBs, which is nothing but configurable logic block followed by switch matrix and IOBs. Only these three elements will be there. CLB means configurable logic block, SM means switch matrix, IOB means input output block. So input output blocks is used for the sake of external connections, whereas the actual logic will be present within the CLB, which is nothing but configurable logic block. And in order to make the necessary connections, we will make use of this switch matrix. Look something like this. Suppose horizontal and vertical interconnects are there. The common point between this two is called as SM, which is nothing but switch matrix. By using this, the necessary connections will be made depending upon our logic functionality. So this is the general structure of FPGA, field programmable gate array. In exam, you need to draw this diagram clearly, like what is meant by switch matrix, what is IOBs, and what are configurable logic blocks. So here logic cell, which is nothing but CLB, configurable logic block, So in order to program this, either 1 or 0 should be given. So generally here it is field. Fpga means it is field programmable gate array. Means field. What is meant by capacitor and what is meant by inductor? How capacitor will store energy and how inductor will store? What is electrostatic and what is magnetostatic? Here capacitor is nothing but electrostatic. It will store energy in the form of electric field. Means once if you charge the capacitor, the information will be stored, which is 1. If you want to store 1, you need to charge the capacitor. If it is 0, it is nothing but discharging. Charging as well as discharging is a concept that will be used for this. So only the CLBs can store either 0 or 1. So in order to store 0, it should be discharged. If it is 1, the capacitor should be charged. Whereas programmable interconnect is used to make the necessary connections, followed by IO blocks for the sake of external connections. And this is the general architecture of FPGA. But in order to understand what is meant by CLBs, you need to know about this lookup table. So just now I told you a CLB. But internally, if you observe within a configurable logic block, it contains LUTs, multiplexers followed by D flip-flop. CLB configurable logic block contains lookup table, multiplexer and D flip-flop. Again, this LUTs varies depending upon the size. Here we are going with 3 input LUT. LUT is nothing but lookup table. And what is the size of this multiplexer? Is it 2:1 or 4:1 or 8:1? What is this? Yes, are you there?
Sir, 2:1, sir.
It is 2:1 multiplexer. And this is nothing but a D flip-flop. So in order to understand the CLB configurable logic block, you need to know some example. So let us take this particular Boolean expression. Some expression is given, which is F1 is equal to x1 bar x2 bar plus x1 x2. So for 2 input combinations, x1 and x2 will get 4 output, which is 0 0 0 1 1 0 and 1 1. So try to substitute within this function and try to write the output. So that F1 I'll get as 1 0 0 1. Now this particular output will be stored in LUT, lookup table. So here this is nothing but a lookup table if you observe. So each and every block is called as a cell, which is used to store either 0 or 1. So as here 4 outputs are there, so better make use of 4 cells. So generally we call them as SRAM cell, static RAM cells, to store the information which can store either 0 or 1. So depending upon the selection lines, output will be given. And here these 3 are nothing but multiplexers which are of size 2-bit. Now I want to check how this is functioning when I apply 0 0. If I apply 0 0, what will be the output? So this is nothing but 0. Here also it is 0. So internally it will be 0 1. This is also 0 1. So if selection line is equal to 0 and I'm storing here as 1 0, this is 0 and 1. Now you tell me what will be the output if selection line is equal to 0 for the first multiplexer. If you are applying selection line is equal to 0, this thing will be connected to the output. So here you are applying 1. Here also same thing, 0 will be connected to the output. Here input is nothing but 0. So here it will be 0 and here it will be 1. Next, what is this x1 connected to? This x1 is connected to 0. So here again internally it will be 0 and 1. Now this 0th pin will be connected to the output, so that I'll get output as 1. You apply the next combinations of input and tell me what will happen. For 1 1 you tell me now.
Sir, can you repeat
For
it
1 1.
again, sir?
Once again. Okay. So this is nothing but a lookup table. So in this I'm storing the information called as 1 0 0 and 1. I'm taking a multiplexer which is of size 2-bit. So 2 input and 1 output. So these are the 2 inputs. Here these are the 2 inputs. And next, what else is missing? Selection line is missing. So apply one selection line here and here. Or else you can take here only directly. So this is one selection line and here again 1 2:1 multiplexer. So these two outputs are connected as the inputs. and one more selection line is connected here, which is nothing but x1. This is nothing but x2. So let us do for 1 1 case. So I'm applying x2 is equal to 1 and x1 is equal to 1. So this point is connected to 1 as well as this is again connected to 1. So internally, if you observe for a 2 cross 1 multiplexer, so we know this one, like it will be I0 followed by I1. Internally it will be 0, 1 and we will get one output y followed by one selection line. Now tell me what will be the output for this first multiplexer?
1.
So if you observe here, this is nothing but 0, 1. Here again it is 0, 1. You are applying the selection line 1. So this thing will be connected to the output. So here output will be 0. Next here again this pin will be connected to the output, but the input that you are applying is 1. So the inputs for this are 0 and 1. Internally you write as 0, 1. Now what is the selection line you are applying? It is 1. So this 1 will be connected to the output. So this 1 will come as the output. The same thing you will get as the output, but you need to represent this one by using a diagram. Means CLB, configurable logic block. It should contain LUTs, lookup tables, followed by multiplexers and D flip-flop. So by using these three elements, you need to explain this. So take any expression that you want, but try to implement this one by using multiplexer. So this concept is same as the one that we have designed by using 4:1 multiplexer using 2 cross 1, or else 8:1 by using 2 cross 1, the same concept. But one more thing that is added here is LUTs, lookup table. Why? Because the information is getting stored in LUTs. Now you tell me for the next case. You explain me this one now. So some random inputs I am applying. Okay, you apply the input combinations and tell. You apply for all 1 1 case. This is 1, this is 1 and this is 1. Tell me the final output or else the intermediate outputs. Selection line is given as 1 for all the first 4 multiplexers. So what will be the output? This 1 will be connected.
It is 1, sir.
So let me write the output. So here it is 1. This is again 1. Here it is 0. Why? Because here 0 you are applying as the input and here it will be 1. Correct?
Yes.
Now apply the next selection line. So next selection line here you are applying as 1.
1.
And again here also you are applying as 1. Now what will be connected? This 1 will be connected and here also 1 will be connected. Now what will be the output?
Output is 1.
Here 1, again here is 1.
1 and 1.
Try to apply the next combination. Next again you are applying 1. Final output will be
1.
1. So this is concept is same as designing the multiplexers. Like you are designing the bigger size multiplexer by using smaller modules. Like 8:1 multiplexer by using 4:1 or else 2:1. Okay, so this much is enough for CPLDs and for Fpga. Generally they will ask you to draw the logic diagram and they will ask you to draw the internals of CLB. So configurable logic block contains LUTs, multiplexers and D flip-flop. Followed by it contains IO blocks followed by switch matrix. Only theoretical part. And better you go for advantages and disadvantages of all CPLDs as well as FPGAs. No need to concentrate anything beyond this. And for PROM, PAL and PLA, try to practice more number of problems. You need to draw the logic diagrams based upon the logic.